In thermochemistry, we're working with path-independent functions. These are also known as state functions. Now, the neat thing about them is it doesn't matter what path you take, because all we care about is the end and the beginning and the distance between the two. One example of that might be me wandering through the classroom. If I decide to take a straight line between the two doors of the classroom, it's a set distance. If I decide to go wandering through the room between those two doors, but also stopping at all the tables along the way, the distance that I walk ends up being a path-dependent function. It really depends on what path I take to decide how long I walk. But if we're talking about the distance between the two doors, the distance between the two doors, path-independent. Doesn't matter how you take to get there, same distance between them. Now, let's change the topic and bring it back to energies, which is what we're talking about in thermochemistry. Suppose that I take a water molecule and an H+. If I want to know how much energy is needed to make one additional OH bond, I can just figure that part out. However, there's another way for me to do that. What I could do instead is actually measure the energy to break each of these bonds, shown here, and then the energy needed to make each of those 3 bonds all over again. And it should give me the exact same answer. Making 1 should give me the same outcome as breaking 2, then making 3. The neat thing about that is it means we can look up the bond association energy in a table somewhere, and from that we'll be able to determine the energy just by adding them all up. That's the great thing that's going to happen from the fact that these are all going to be path-independent changes. Now that also means the energy consumed in growing a plant is going to be the same energy that we get back when we burn the plant, because one is going to be a combustion reaction, burning the plant, and in a combustion reaction we're going to take all those sugars and everything, plus oxygen, to yield carbon dioxide and water. When we take carbon dioxide and water, remember what a plant needs to grow? It uses carbon dioxide and water to make all those fibers and things that were inside of the plant in the first place. So that's another example of a path-independent change. That said, there's going to be lots of waypoints along the way, and so you're going to need lots of extra materials. One path will certainly be a lot more simple for you to do the calculations. This is certainly more complicated to calculate than this is, but sometimes you can't directly look at this reaction. Well, a reaction like that one at least. Sometimes you actually have to do it in a more complicated way, and we'll see examples of that throughout the chapter, especially when we talk about Hess's law.